And in the third part, I'd like to talk about propositional logic. Okay, as I said, every formal logic system consists of three components. First is the syntax, then there is the semantics, and the third component is the proof theory. So let's start with syntax, then we talk about semantics, but proof theory we leave for next week since this is about inference, and we'll talk about automated inference next week. So syntax first. Syntax is very simple in case of propositional logic. First, we need to define the alphabet. What are the things that we are working with that constitute the building blocks of the formulas. So these are the symbols of propositional logic. First, we're going to have a set of so-called variables, propositional variables or atomic formulas, and we'll use uppercase letters for these. And let's denote with V the set of these formulas. Variables. Then we're going to have logical operators, so the connectives for negation, for the OR operation, and implication and equivalence. And we are going to introduce two logical constants, true and false, which basically denote a proposition that it's always true or false, respectively. And finally, we need parentheses in order to be able to group the formulas and build larger formulas. Okay. Now, once we have the alphabet, we need to define the grammar. Essentially, the grammar is defining what are the valid strings of the language, right? So in this case, what are the syntactically valid formulas? And the syntactically valid formulas are called well-formed formulas, or WFF. A well-formed formula, or simply we just call it the formula of propositional logic, is defined recursively using the following four rules of grammar. First, an atom is a formula. And then once we have a formula F, we can always simply just put a negation in front and parentheses around it, and this is going to be a well-formed formula as well. And if F and G are formulas, then the following four strings are going to be formulas as well. We are basically building a conjunction, right? A formula conjoined with an AND operator, or a disjunction of two formulas, or an implication, or an equivalence. And finally, there's a closure rule that is saying essentially nothing else is a formula. Now, in order to simplify convention and to increase readability, essentially, we're going to introduce simplifying conventions. We're going to drop parentheses in rule number 2, so these two can be dropped. And we're also going to drop parentheses in 3. So the surrounding parentheses around binary operator application, if they are the outer parentheses of the formula. Okay. Let's look at a couple of very simple examples of formulas. So, for example, these four guys here are atoms, right? The simplest formulas we can have. Again, an atom here, but a negated atom is a formula as well. This is a formula as well, built using disjunction here, and then a negation, and then again a disjunction to give me a more complex, a compound formula. And the other two examples as well. Okay, so this is syntax, right? But so far we didn't talk about what these formulas mean, right? And in order to talk about the meaning of formulas, we need to introduce semantics, which is the second component of a formal system. So, with semantics, then we can, maybe talk about A meaning something, like A is meaning the earth is round, and B is meaning Harry Potter attends the Hogwarts School of Witchcraft, and, and so forth and so forth. Now, but the meaning that is associated with the atoms and with the formulas later actually comes from semantics, obviously, not syntax. So let's talk about semantics. Now, semantics starts with the idea of an interpretation. Interpretation is essentially telling us which of the variables or atoms in my formula are true and which of them are false, right? And once I have this is going to be the truth assignment to each variable in my formula. I can start talking about the entire formula being true or false. So let's make this more formal. So let's F be a formula which is well formed. Now this is important, right? Because you have to have syntax right before you continue go on talking about semantics. So the formula F has to be syntactically valid or well formed. And then let's V be the set of propositional variables or atoms that are occurring in the formula E1, E2 through En. And then I'll be defining interpretation as essentially a function. And the function is assigning to each variable from V a truth value, which can be either true, denoted with a T here, or false, denoted with a turnstile T. With an inverted T. So this basically function assigns to each variable from V a truth value, either true or false, right? Okay. Now, if my formula has n atoms, then if you think about all the possible combinations there, it's going to be 2 to the power of n, since each and every variable can be either true or false, right, on or off. So a formula then with n interpretation will always have 2 to the power of n different interpretations, so different I functions. Now, when we talk about using formal logic for representing knowledge in AI, it makes sense to talk about or to think about interpretation I as describing one possible world situation. The world situation is characterized then by certain variables being true and certain other variables being false. Let's go back to the example that we had here, for example, right? So, if I'm essentially saying this, this is my formula here. So, there's 3 variables here, right? So there's going to be 2 to the power of 3, which is 8 different interpretations. And in one of these interpretations, A can be true, B can be false, and C can be true, for example. And this particular interpretation, where A is true, B is false, and C is true, for example, is essentially corresponding to one world situation. Okay, we'll talk about world situations again in a moment. Before that, let's look into how to derive or evaluate the truth value of the entire formula, right? So if I have, let's go back again to the example here. If I have the truth values for A, B, and C, and these are defined by the interpretation function, then I'd probably be interested in knowing what is the truth value of the entire formula here. So say if A is true and B is false and C is true, well then I know actually this should be true then, because there's an OR operator, and if this is true, then the negated value of this is going to be false, but I have true or false, so the entire formula turns out to be true. So I'd like to be able to do something like this, and for this to work, I obviously need to define the semantics of the operators, and then starting from the value, the truth value of the variables as defined by the interpretation function, I'm going to build the truth value of the entire formula by essentially going bottom up and applying the semantics of the operators. Okay, so let's try to define this. First, we need to define how the operators work, and this is done by means of the truth table. And I would say and assume that you are familiar with these truth tables from all previous courses. The idea here is that we essentially say, okay, if I have F and G as formulas, then there is going to be 4 possible interpretations, 4 possible assignments of truth value to these 2 variables, and then I'm defining the semantics of each of these operators, the negated F, the F and G, F or G, and F implies G, and F equivalents to G. And I would say that you are probably familiar with all these since these operators actually follow quite closely the semantics of natural language. So when we say and, we mean both need to be true, and when we say or, we essentially mean at least one of these has to be true, and so forth. So I'd say these are intuitive because they actually correspond to the semantics of natural language, except maybe for the implication operator here. The implication operator does not always follow the semantics of natural language, and I guess the problem here is that we somehow expect semantics to model causality, like if F causes G, but this need not be the case. So it makes sense really to make sure that you understand how semantics works. And the way it works is, if F is false, then semantics of F implies G is going to be true, regardless of the value of G. But if F is true, then the only combination that I'm not allowing, which should be evaluating to false, is if G is false. Otherwise, if G is true, then the whole implication is true as well. In an implication, F implies G, we'll call F the antecedent, and we call G the consequent, right? So essentially, the semantics of implication is such that if the antecedent is true, then the consequent should be true as well. So the only combination in which implication is false is if the antecedent is true and the consequence is false, right? So this then, let me clean this up a bit. This interpretation, the third one, is the one for which you should know that the implication evaluates to false. Of course, do not think of this as a third interpretation truth table, because the order can be altered. Think about, again, the case where antecedents is true and consequence is false. This shouldn't be the case. That should be evaluating to false. I said that the implication operator actually doesn't really always have an intuitive semantics. And to give you an example, consider a statement like, if the earth is flat, then, then Croatia is larger than the United States, right? Now, is this true? Well, I'm saying if the earth is flat, let's denote it with F, then Croatia is larger than United States. Let's denote that with C. Now, it's true, actually, since, the earth is not flat. And then, this is the case of these two interpretations here. And you see, regardless of the consequent, regardless of the truth value of the consequent, the implication is true. So, if the earth is flat, then you can say whatever you want, since, the earth's not flat. And at least I hope we are agreeing on this one. This seems to be sort of counterintuitive, and that's why in logic we typically call this material implication, just to know that it's sort of different from everyday implication. But the property of implication being true if the antecedent is false is actually going to come in very handy when we formalize natural language inference sentences using logic, as you're going to see in the fifth part of today's lecture. Okay, good. So once we have the semantics of the operators defined, the unary negation operator and the binary operators of and, or, implication, and equivalence, we can go on to define the truth value of the entire formula, which essentially does, what we've shown earlier, basically building bottom up. We go bottom up and build the truth value of the entire formula. The way we do this, well, recursively, given an interpretation I and the formula F, which needs to be well defined, well-formed, we sort of extend now the domain of the I interpretation function to also be defined for formulas, not only atoms. And essentially we say, if the formula is just a true constant, it should be evaluated as a true formula. If it's false, it should be evaluated as false. If it's a formula that contains a negation, then evaluate the formula, but then, after you're done, just negate. And if the formula is a disjunction, then evaluate each of the subformulas and then just do the OR operation as defined by the table from the previous slide. And similarly, if the formula is a conjunction, again, dive in and evaluate the formula, the first subformula and the second, and then just combine them using the semantics of the AND operator as defined by the table from the previous slide. So the way this works then is, for example, let's assume we have a formula like this one, a bit more complex. And now we'd like to know what is the truth value, right? We'd like to evaluate this formula. Now, the first thing that you have to have in mind is that the question of the truth value of a formula doesn't really make sense unless you're given an interpretation. Because it's only in an interpretation or, with respect to an interpretation that the formula has truth value. So I need to give you two things then. I need to give you a formula and I need to give you an interpretation. So the formula's here, right? This is the formula. But now, there is the interpretation and this is the interpretation. The interpretation is assigning the truth value to variables. And since there is only 3 of them in my formula, I only need to define truth values for the 3 variables, right? And in this particular case, the interpretation is assigning false to A, true to B, and true to C. And note that this is actually one of the 8 possible interpretations for this formula. So what we do now, we apply essentially this recursive formula here. We apply I interpretation function to the entire formula. And what we need to do then, we will decompose the formula based on AND, which essentially means this is the rule we are applying. So I is applied to this part of the formula and to this part of the formula. And then, we go on and dive in deeper until we end with I being applied to the variables or atoms, the value of which we can read off from the interpretation function as defined initially. Once we have these things, right, we will now substitute false here for the interpretation of A, true for interpretation B, and so forth. And then we would be applying the semantics of the operators and go bottom up. And finally, we'd arrive at the value of the truth value for the entire formula. Okay, I hope that made sense. Another concept that I'd like to introduce, a very important one, is a model. A model is just one kind of interpretation, specific interpretation. Recall that interpretation is actually an assignment of truth values to all variables in a formula. Now, an interpretation will be a model of a formula if and only if the formula is true for that particular interpretation. Or in other words, if the interpretation satisfies the formula, then that particular interpretation will be called a model. Okay. And now a model actually, an interpretation describes a state of the world, and a model describes a state of the world as explained or, as stipulated, as asserted by a formula. And it is very useful to think of models in that way. So a model is essentially how the world is according to the formula. Let's look at a couple of examples. For example, if I give you a formula not A or D, let's A stand for the earth is not round. Oh, sorry, A is standing for the earth is round, and D for Minotaur is a mythical creature. Then this particular formula is actually describing a situation, right? Now, why? Because this formula has 2 interpretations, because it has 2 variables, right? And out of these, it has 4 interpretations because it has 2 variables. And out of these 4 interpretations, Some of them are going to be, in some of them the formula is going to be true, and in others it's going to be false, right? So what are the interpretations in which this particular formula is true? Well, A has to be true when negated, and D has to be true. So A has to be false, and D has to be true, right? And this is the only interpretation out of 4 possible for which this formula is true. And this interpretation is the model of the formula, right? So it's the interpretation, in this case it's 1 out of 4, for which this particular formula is true. Okay, and now the idea is that you can think of this interpretation, the model, which makes the interpretation true, the model, as the world situation as described by the formula, right? So the formula is essentially saying, the world is such that A is false and D is true. Or in other words, the earth is not round and Minotaur is a mythical creature. Okay? Cool. Now, in this example, there was just a single model for the formula, but a single formula may have a number of models. And in this case, you can think of the formula describing a set of possible world situations. Like, we are not certain how the world actually is, but there is a set of hypotheses about how the world might look like. Okay, and these hypotheses then are the different models for the formula. So for example, if we have a formula A or D, well then this formula has several models, right? Which ones? Well, first off, how many interpretations we have for this formula? We got 2 variables, right? So it's going to be 2 to the power of 2 possible interpretations, which is 4. And out of these 4, there is 3 interpretations that actually make the formula true. So it's 3 models out of 4 interpretations, right? And these are A is true and D is true, A is true, D is false, and A is false, D is true, right? The only interpretation for which the formula is not true, or in other words, the only interpretation which is not the model of the formula, is the one in which both A and D are false. Right, so since there's 3 models for this formula, then in a way this formula describes the world using 3 world situations in which A and D are both true, or just one of them is true. I'm not certain, I'm not sure about how the world looks like. All these 3 are possible. The only situation that's not possible is for both A and D to be false, since this interpretation is not a model of my formula. Okay? Good. The basic terms that need to be defined when we talk about semantics are validity, inconsistency, and satisfiability. Validity, or formula is being valid if and only if it is true in all interpretations. So now think of a formula and it's 2 to the power of n interpretations, and you would be able to list all these interpretations in a truth table, going, enumerating all the combinations. And if it turns out that when you evaluate the formula for each and every of these interpretations, you always end up with the formula being true, then this is a valid formula or tautology, a formula that's always true regardless of how you tweak the truth value of the individual variables. Then the opposite is to have an inconsistent formula. An inconsistent formula is a formula which is never true in none of the interpretations, also known as a contradiction, an unsatisfiable formula, anti-tautology. And finally, in between these 2 extremes, formulas are going to be satisfiable, which basically means, well, they are true for some of the interpretations, but not necessarily for all. So a formula is satisfiable or consistent if and only if it is true for at least one interpretation. Okay, and if it's true for all interpretations, it's of course again still satisfiable, but it's also a valid formula. Okay, and now if you would take a couple of minutes and think about what this means, if a formula is valid, if it's not valid, it's inconsistent, if it's valid, then it's satisfiable. If it's not satisfiable, then it's inconsistent. You actually would be able to build like a small graph of the relations between these three concepts, but we'll do this for you with a couple of statements here. So first, a formula is consistent if and only if it's not inconsistent. A formula is valid if and only if its negation is inconsistent, and so forth. It doesn't really make sense to learn these by heart. You just need to know what the individual concepts of validity, inconsistency, and satisfiability mean. But what is helpful is actually this figure here, where basically we need to know that there is a set of formulas that we can satisfy, and all of these that we cannot satisfy are inconsistent, and within the set of satisfiable formulas, some of them are valid, right? So I guess this statement is probably the most important one. If a formula is not inconsistent, then it is consistent or satisfiable, but it need not be valid, since valid formulas are just a subset of satisfiable or consistent formulas. Okay. Now let's see if this actually came across, and I'll give you a couple of formulas here, propositional formulas, and ask you about, for each of these, to tell me if this is a valid formula or if it's a contradiction or if it's a satisfiable formula, right? And of course, if it's valid, then it is also satisfiable. Okay, so what about the formula P? Is this a valid formula, a contradiction, or a satisfiable or consistent formula? Well, you have to think about the interpretations, all the interpretations of the formula, and then evaluate the formula in each of these interpretations. How many interpretations have we got for this formula? Well, there's only one variable, so it's going to be two possible interpretations where P is true or P is false. And since P can be true or P can be false, the formula then has to be, satisfiable. Sometimes it's true, sometimes it's false, so a satisfiable formula. What about P or Q? Well, there is two variables here, and therefore there is four interpretations, and we know how the OR operator, the semantics of OR operator works. We know that there is going to be three models out of four interpretations, but not all four interpretations evaluate the formula to true. But there is three of those which do, so the formula is satisfiable, right? Not always true, not always false. What about not P or Q? Well, it's the negated formula from the one above. And since in the previous case, we had a case where one interpretation was false, for one interpretation the formula was false, for three it was true. With the negated version of the formula, it's going to be the opposite, so we're going to have one interpretation in which the formula is true and three in which it is false. So one model out of four interpretations. But again, it's not the case the formula is always false, it's not always true, therefore it is satisfiable as well. What about this one, not P or P? Well, this is a different kind of beast here because, how many interpretations have we got here? We got there's just one variable here. Okay, so don't be fooled by the fact that P is being repeated or mentioned twice. We are interested in the number of unique variables, and it's just one, it's P, right? So there's two interpretations. P can be either true or false. And if P is true, let's see what's the truth value of the formula. If P is true, then not P is false, and P is going to be and true. So we're going to have false and true, which will evaluate to false according to the semantics of the AND operator. But then if P is false, then we'll end up with true or false, which is again false, right? So in both cases, both interpretations, and there's only two of them, the formula is false. Which essentially means the formula is a contradiction, right? Now this particular formula is what we call a law of contradiction, right? Not P and P cannot be the case. So it's a contradiction or an inconsistent formula or anti-tautology. What about the next formula here, P or P? P and P. Well, again, it's just one variable. This is actually turns out to be equivalent to P, right? There is two interpretations. P can be either true or false. Well, if it's true, then it's true. If it's false, it's false. And this formula is actually equivalent to the first one we had here, and it's satisfiable. Can be true, can be false. What about the next one? P implies Q. Well, P implies Q, it's an implication, and we know from the truth table of an implication, but let's have it here again, that the resulting implication, the truth value of the implication looks like this, right? This is true, this is true, this is false, this is true. So we have a case here where there is one interpretation, namely this one, where the formula is false, but there is 3 models out of 4 interpretations, so which means the formula is satisfiable. P or not P. Again, only 2 interpretations. P can be either true or false, and if P is true, then the formula is going to be true. If P is false, the formula is going to be true again. So, the formula is always true, which makes it a valid formula, right? By the way, this formula is called the law of excluded middle, essentially saying, it's either P or not P. There cannot be anything else, or tertium non datur in Latin. Okay. What about P implies Q and P? Now, this is slightly more complex, and in this case, I would actually start by doing a truth table here. There is four interpretations again to this formula. Okay. And P implies Q. This is true, this is true, this is false, this is true, right? And now I need to combine this and P, right? So if I combine this, so I'm now combining these two guys using an AND operator here. And what I get is, well, true and false and true is false, this is false, this is false, and this is true, right? So I ended up with a formula which is got 1 model out of 4, and therefore the formula is satisfiable. I would do a similar thing here with this formula, drawing a truth table, and it would turn out to be a valid formula, and also for the rest as well. What about the last one, P or Q? P equivalent to Q. P equivalent to Q. Now, if you go back and look at the semantics of the equivalence operator, you'll realize that the formula is going to be true if both P are true, or both P and Q are true, or both P and Q are false. So there is 2 models out of 4 interpretations, which makes the formula satisfiable. Okay. And another concept that is actually quite useful is that of equivalence, quite an intuitive one. A formula F is equivalent to another formula G, and this will denote with F equivalent to G if and only if the truth values of F and G coincide, if they are the same for each and every possible interpretation of F and G, right? Okay, one thing to note here is the difference between this notation here and this notation. What's the difference? The difference is that F equivalent to G, and the spelling is actually, the way you read it out is the same. F equivalent to G, the left-hand side version, is actually a formula of propositional logic. So it itself got a truth value. It can be either true or false. F equivalent to G is not a formula. The right-hand side here is not a formula of first-order logic, since this particular symbol here is not belonging to the syntax of propositional logic, right? So it's sort of a meta statement. It's a statement about 2 formulas made outside of the system of formal logic. But there is a clear relation between these two. If this equivalence formula is valid, this basically means that F equivalent to G holds and vice versa. So F equivalent to G is valid if and only if this holds. And right. Okay. There's a bunch of equivalences in propositional logic commonly used when you do logic, and also some of them we'll need for automated reasoning next week. So I'd like to maybe discuss these quickly. So first there is the involution. Involution, basically this one. Involution means if I negate twice, I get the non-negated, the affirmed formula, right? And the other very important formula here is the second one, which allows me to replace an implication with a formula where I basically have a disjunction of the negated antecedent or a consequence, a consequent. Another quite useful formula is this one, where I can replace an equivalence. Maybe, version number 7 is actually what I'd like to use. So an equivalence is like an implication that goes both ways, and then I can use 2 to get rid of implications as well. And as you're gonna see next week, we actually would want to get rid of equivalence and implications and try to rewrite our formula in terms of the more basic operations of negation, the AND operator and the OR operator. Also important is the idempotence here. It essentially tells me, G and G is equivalent to G. No need to duplicate the formulas in a conjunction, and the same here holds for the OR operation, and this particular equivalence is called factorization. There is a law of contradiction which we mentioned. G and not G is equivalent to false, right? And on the next slide, there's more, but just a couple of them actually we'll be needing. I'd also like to mention the law of excluded middle. We already mentioned this. So G or not G is true. So there is no third option in the world of propositional logic. And associativity holds as well. This essentially means, so it's 17 and 18. So this essentially means that in a series of identical operators, I can replace the parentheses. So the order in which I do the operation doesn't matter, and it holds for the AND operator as well as for the OR operator. Commutativity holds as well. I guess you knew that from before. Distributivity will be needing as well. Distributivity essentially means that I can factor this formula into 2 by regrouping F. So I will be combining F with the outer operator and G, and then F with outer operator and H, and then conjoin these two with the inner operator. Now this is like in math, where we would have distributivity of a product over a summation, but in logic the distributivity also holds the other way around. So it's the distributivity of the AND operator over the OR operator holds as well. And lastly, very important 2 laws which I guess you're familiar with from other courses are the De Morgan's laws that allow me to negate a formula from the outside and push negation toward atoms, essentially. So a negated F or G is just flipping the operator and negating both subformulas, and similarly negated F and G is going to flip the operator and negate both formulas. Okay. I guess you are familiar with most of these equations. You don't need to know them by heart. You can always, of course, if you ever need to, you can prove them using semantic tables and going through all the interpretations, and to convince yourself that the left-hand side is indeed equivalent to the right-hand side. But you don't need to do this because you will be allowed to have a list of these formulas. But nonetheless, it actually makes sense to familiarize yourself with some of these, since this will give you a bit more of confidence when you solve problems from logic. I'd just like to go back for a second and talk about involution here. So the point here is that all these equivalences are actually very well known and accepted, and we use them when we do logic. But don't think of them as something that is set in stone, since there have been approaches in philosophy and logic as well that actually decided not to commit to one of these equivalences. For example, there is the intuitionistic logic or constructivist logic, in which basically the equivalence number one, the involution, or the idea that double negation affirms, is not accepted. And as a consequence, then, everything else is then slightly different in this kind of logic. For example, the law of excluded middle, number 16, is also not holding in that kind of logic. And yeah, so, the point here is that there's different kind of logics out there, and for some of them make different assumptions. But the kind of logic we're going to use, the good old propositional logic, is actually using involution, and we'll be using involution a lot. Okay, and now the last and central concept here of propositional logic I'd like to talk about is the concept of logical consequence. Logical consequence is the motivation for logic. It's why I'm actually bothering to do logic. Because I like to be able to talk about logical consequences. Logical consequence is telling me what is the conclusion that follows from a set of premises, a set of given facts, set of formulas that I have as input. And here's the definition of a logical consequence, and I'll guide you through the definition, and then we'll look at a couple of examples, and I think it will make perfect sense. So let's look at the definition first. A formula G here will be a logical consequence, also known as a semantic consequence, since we're talking about semantics now, of a set of formulas f1 through fn, if and only if every interpretation that satisfies the set of formulas f from 1 through n simultaneously, so f1 and f2 and f2 and f3 and f4 and so forth and fn, also satisfies G. Okay, so I need to have a situation where whenever my formulas f1 through fn are satisfied, which is to say are true, then G has to be true as well. And if this is the case for all interpretations, then I can say that G is the logical consequence of the set of formulas f1 through fn. Okay? Or in other words, if I now start talking about models and recall that a model is an interpretation that makes a formula true, then I can say that a formula G is a logical consequence of a set of formulas f1 through fn, if and only if every model of the formulas f1 and f2 and so forth and fn is also a model of G. Okay. Now, intuitively, what this means is, whenever these formulas f are true, then I definitely know that G has to be true as well, if G is the logical consequence. And it's actually quite a strong relation. I can learn about the truth value of G based on the truth value of f. So there seems to be some connection between them, and that's the connection is that of a logical consequence. We'll also introduce some notational machinery here, and I will be denoting the fact that G is a logical consequence of these sets of formulas using the symbol here, which is a double turnstile T symbol. So whatever here is on the left hand side is the set of premises, and separated by commas, and on the right hand side I'll have a formula that is the logical consequence of the set of formulas from the left hand side. Okay, and the way I'm going to read this is f1, f2 through fn logically or semantically entails formula G, or G is semantically entailed from formulas f1 through fn. Okay, so that's the formal definition. I hope it makes halfway at least sense. Now let's look at an example. Here's an example. I'd like to be able to show, right, that Q here is the logical consequence of two formulas, P or Q, and not P, right? I'd like to be able to show this, right? Now let's come up with an example ad hoc. So I don't know. Imagine that I'm basically saying today is April. Well, or maybe no. The Earth is flat. Let's have P for the Earth is flat, or today is April, right? And then you learn that the Earth is not flat. And then you'd like to conclude that today is April. So if I'm telling you, the Earth is flat or today is April, and I'm basically telling you, it's either both or, one of these, and then you learn, okay, the Earth is not flat, then, the only thing that you're left with is that today is April. So, intuitively, this should actually, be the case. And indeed, Q should be the logical consequence of these two formulas. Now let's show this formally. And since the logical consequence is defined in terms of interpretations, we have to think in terms of a truth table and semantics. So what we do is, here we actually have two variables in the game, P and Q. So it's going to be 2 to the power of 2, which is 4 interpretations for these formulas. And we essentially now enumerate all these 4 interpretations, and then start building the truth value, evaluating the truth value of the two premises, the two input formulas. Let's see, right? So this is the first formula, and for not P, we simply negate this column to get this. And now, if Q here, which is just a copy paste of this column, if Q is indeed the logical consequence of these two formulas, then it has to be the case that whenever the two formulas, this one and this one, are true, Q has to be true as well, right? And if you look at the 4 interpretations, the only case where the two formulas are true is actually this one here. So, there's just one model for the two formulas out of 4 interpretations. And it is actually the case that the interpretation that makes these two formulas true is also making the Q formula true as well. So whichever interpretation is a model for the premises, the same interpretation is also a model for the Q formula. So yes, the Q formula here is a logical consequence of these two formulas. So this relation here actually holds. Okay, so note here that we actually got 4 interpretations, but we only zoomed into this one interpretation that actually is the model for my premises. In this particular case, it was just one, but generally you can have more interpretations that are models for your premises. And the other thing to note is that Q actually was true in some other interpretations as well. Here, for example, in the last one, but we don't care, right? Since this is not covered by the definition of a logical consequence. Logical consequence is just about checking if all the interpretations that are making the premises true are also making the logical consequence, the alleged logical consequence true. And if this is the case, then yeah, this is a logical consequence. I don't care about the cases where the logical consequence is true and the premises are not. And not an issue, doesn't really hurt, but I don't care about these cases. Okay, cool. A couple of words about the relation between the notion of logical consequence and validity on one hand side and inconsistency on the other. I will be denoting, so I actually said that I will be denoting with F double turnstile G the situation where F semantically entails G, or G is the logical consequence of F. But here's another piece of notation. This here will denote that F is a valid formula. So you can think of this as, F being semantically entailed from an empty set of formulas. So it is true regardless of the premises. Now, by the definition of logical consequence, a valid formula is logically entailed by any premise, including an empty set of premises, right? So if I have formula f, and if I'm now telling you, f is always true, regardless of the interpretation, well then, whatever you have here, it is going to make your relation true, right? Because it will always be the case whenever your set of premises is true, f is going to be true as well, because of the simple fact that f is a valid formula. It's always true, right? So you see, a valid formula then is logically entailed by any premise. To give you an example, this thing here, P or not P, we already said that's a valid formula, it's always true. Well, you can have whatever you want on the left-hand side here. It will always be entailed from whatever, right? Now, this is actually interesting, but it's not very useful in practice. Basically, it tells us, if the formula is true, it could have come from whatever. And when we do reasoning later, an automated reasoning AI, we'll actually try to avoid these cases in which we derive valid formulas, since it's not really any new piece of knowledge, since we all know that a valid formula is always logically entailed. And conversely, also by the definition of a logical consequence, an inconsistent formula, a contradiction, logically entails any formula. Now, why is this the case? Well, if I have a formula here, f, which is, always always false, then you can have whatever you want here, since it will never be the case that the formula f has a model, right? And you never need to check. There is no interpretation you need to check, because the logical consequence is telling you whenever you have an interpretation that is actually a model of the formula, you have to check if that interpretation makes x true as well. But if it's never the case that an interpretation is a model of a formula f, there's nothing for you to check, and the definition actually goes true, and this actually holds, right? So for example, if you have a formula p and not p, which we said earlier is contradiction, right? It's always false, then you can have whatever you want on the right hand side, okay? And now, following the same reasoning as with the first case, we realize it's actually quite useless in practice to start the inference from a set of formulas that are inconsistent. Since if you have an inconsistent set of formulas, you can derive whatever, and it will be a logical consequence. So you see, there is these two cases that are actually legit, but we like to avoid them when we do practical, when we do automated reasoning later next week. We'd like to avoid the cases where we derive valid formulas, and also we absolutely like to avoid the cases where the set of premises that we start out from is inconsistent in itself. Okay, keep that in mind, and we'll talk about it next week. Okay, how do we prove logical consequences? Well, there's two ways, the so-called direct method, and the other one is the proof by refutation. Quite simple ideas. Let's look at definitions first, and then we go through an example together. The direct method is actually directly applying the definition of a logical consequence, where we said, the formula is a logical consequence if it's true whenever the premises are true, right? So a formula G is a logical consequence of a set of formulas if and only if this holds. Because if this holds, if this is true, for every interpretation, it has to be valid. If this formula is valid or in other words, if it's true for every interpretation, then this exactly captures the definition of a logical consequence, right? Since in this case, G will be true whenever these guys here are true together, right? So in other words, the relation of semantic consequence here holds if and only if this implication here is valid or true for all interpretations. The relation between, the definition of a logical consequence and the validity of the corresponding implication is called the semantic deduction theorem. Okay. So that's one way then to prove things, to construct this implication here and show that it's a valid formula. The alternative is to resort to refutation. Refutation essentially means that I will negate the alleged logical consequence and show that it doesn't lead me anywhere, right? And then I'll have to back off and say, okay, sorry, actually G was the logical consequence. More formally, what I'm doing here is, I'll actually like to prove this. This is what I would prove with the direct method which we just introduced. And we said this would have to be valid, right? Now, if this has to be valid, then its negation should be what? Should be inconsistent, right? Or contradiction. So you go with negating this formula. And if you negate this formula, now here we are now. If you negate this formula and apply, a set of equivalences, you would eliminate the implication by essentially, using this rule. This is equivalent to not F. Sorry. This should be, let's do this again. This should be F implies G is equivalent to not F, or this should be an or G, right? And then you would use the De Morgan's law to push the negation closer to the variables. You'll end up with this, okay? And now you're basically saying, okay, this should be inconsistent, right? Because I negated something that should have been valid. And if this is inconsistent, then the same as saying this is valid, then G is the logical consequence. So, but now if you look at this thing here, this is essentially telling us, it cannot be the case that all these premises are true and that the logical consequence isn't true. So this cannot be the case. And therefore, G has to be true when the premises are true. And therefore, by the definition of the logical consequence, G is the logical consequence of the set of formulas F, right? Okay, so more formally, formula G is the logical consequence of the set of formulas from F1 through Fn if and only if this formula here is inconsistent or contradiction or, false for all interpretations. And in other words, in order to prove that G is the semantic consequence of the set of formulas from F1 through Fn, we have to show that this holds, and this means that this formula here is valid, and its negation then, the inner one, has to be inconsistent. Okay, so in practice, what you would do, you essentially take the set of premises and you combine it with the negated formula that you'd like to prove if it's a logical consequence. And then you go on trying to prove that you'll end up with an inconsistent formula, a formula that's always false. Okay. We'll actually do these things next week as well. Okay, now let's look at an example. Let's try to prove P or Q and P semantically or logically entails Q. We already said this is the case. We looked at an example. We actually followed the definition of a logical consequence and convinced ourselves that this is the case. But now let's do the proofs. Let's do the direct proof first and then proof by refutation second. So the direct proof essentially means I need to construct again a table. There's going to be, since there is two variables involved, there's going to be 4 interpretations which I am enumerating here. And what I need to do is I need to construct an implication from these premises to Q. So my implication is going to be P or Q. That's my first formula. And not P. And then I'm saying, okay, all these guys are implying Q. And if this turns out to be valid, then yes, Q is a logical consequence. And now, in order to show that this formula is valid, I'm actually building the table here. So going through the 4 combinations here, the 4 interpretations, and then evaluating the truth value of the first formula, of the second formula, which is essentially just the negated first column, and then combining them together with an AND operator. So I'm combining these two guys together to give me this column, okay? And finally, I'm constructing an implication from this formula. Let's denote it F to Q, and I have it here. And yeah, let's do this together now. Let's clean this up a bit. So I'm going to build an implication from here to here, right? Like this. Okay. So this is false. If this is false, remember, keep in mind that the implication is true. This is true. Well, then I have to check the consequent. Oh, it turns out to be true as well. So this is true. This is false. I don't care about the consequent. The implication is true. This is false. I don't care about the consequent. The implication is true. So I ended up with a formula that's true in each of the 4 interpretations. So all 4 interpretations are actually models of this formula. And then by the definition of the direct proof, this actually means that Q is the logical consequence of these 2 formulas. Okay. Similarly, if I do proof by refutation, my goal here will be now to take these 2 formulas, P or Q. That's my first formula, and the other formula is not P, right? And take the negated alleged logical consequence. And now I'd like to show that this is inconsistent. It cannot be the case. It's always false for all 4 interpretations. Again, I'm going to do this by by enumerating all the cases, by essentially filling in the semantic table here. Now this part's the same as what we had here, right? This is the same. And I'm now negating the Q, the alleged consequence here. I'm essentially taking this column and just negating it, and it's here. And now I need to show that if I combine these 2 columns with an AND, and that's what I'm doing here, I'll end up with a formula that's always false, which is a contradiction, right? And this then, by the definition of proof by refutation, proves that Q is the logical consequence of these 2 formulas. Okay, so I hope that made sense. The point here for you to remember is that you need to go through all these interpretations in your table of all the variables that you have in the relation that you like to prove, and essentially you go either by try to prove that the implication is always true, a valid formula, or it's always false, inconsistent formula. This then brings us to the second, more complex formalism of logic, the first order logic.